Hello from Minnesota, and welcome to this little talk about RISC-V verification. I'm Bill McSpadden, and I'm a principal verification engineer at Seagate. Our team at Seagate has developed several RISC-V cores for use in hard disk drive controllers. This summit is a little bit of a coming out party for us. We have several Seagate presentations that I hope you'll take a look at. The first is John Morris's keynote address. The second is Richard Bond's presentation on the architecture and design of our cores. And the third is Manuel Offenberg's discussion of one of our cores where it's being used in a secure application environment. I joined the team rather late in the development process. Much hard work had already been done by the time I joined. But I get the privilege of sharing with you what we did to verify these cores. The title of my talk is Comprehensive Pre-Silicon Verification of RISC-V Cores in a Storage Controller. This is a short outline of what we'll talk about today. The problem that we ran into at Seagate, the solution that we came up with, which leads to a bit of a verification problem, which then leads to a verification solution. And what was the final result? What can we say about our development of our RISC-V cores? The problem. I'm sure many of you have run into this. What do you do when your processor runs out of oomph? The issue that we had was with the servo controller application. And it is the benchmark, it's the application that drove the design. It's math intensive. Real-time computation with fixed temporal boundaries. The servo processor performance was about to max out. We could see it, the writing on the wall. We only had a few more years left before we were going to have to come up with a real solution, or we were going to hit the wall. And improvements to the current processor family did not look like they were going to meet our needs. So, what was the solution? And how did this solution create a verification problem? Tomorrow, Richard Bond is going to give a talk about the architecture and design of our RISC-V cores. I'd encourage you to attend his talk to get more details about the history of the development and for more details about the design. For the purposes of this talk, I'm only going to give you the high-level details about our cores. The first of our cores is a high-performance core. It's an aggressive, out-of-order, multi-issue core. It's a 32-bit implementation with the I, M, F, C, and N extensions. We have machine and user modes. It's a speculative out-of-order pipeline, 4-wide fetch and dispatch, 8-wide issue. High-performance instruction fetch, branch prediction, return address stack, loop buffer, a dual-ported load store unit, tightly integrated memories at the L1 level, multi-way L1 caches. We have an FPU in the design and a platform level interrupt controller, a PLIC. We have native ECC port support. And we have the RISC-V debug and trace implementations as defined by the RISC-V groups, also implemented in our cores. Now, if we're going to develop a high-performance core for the servo controller, how hard would it be to develop a simple, small controller to replace our other controllers? Well, someone at Seagate asked that question, and the answer was it wasn't all that hard, so we went ahead and developed another core as well. It's an area-optimized core. We have both 32 and 64-bit versions of the core that implement the I, M, C, B, and N extensions. We don't have floating point in this. We did add a bitmanip function, bitmanip extension. It has machine, supervisor, and user modes. We have virtual memory support for both SV39 and SV32. We have a 5-stage single-issue in-order pipeline. We also implemented a click. We have enhanced PMPs. The focus on at least one of these cores was on security features, and Manuel Offenberg will talk to you about those in another presentation. Again, in this core we have native ECC support and we have RISC-V debug. This leads to one very serious verification problem, and for those of you who are verification engineers, you know what's coming. The permutations of configurations. How many different configurations, how many different architectures, how many extensions, how many whirl bits, how many things do we actually have to test? The permutations are very large. Take a minute and give a little perspective on where we've come in the industry. I want to go back to 1981 and look at a quote from Edson de Castro in the book The Soul of a New Machine by Tracy Kidder. I came into the industry in 1983, working for Intel, about the time the book came out. It's the story of the development of Data General's Eclipse minicomputer. The book is a fun read for all sorts of reasons: office politics, technical problems, interpersonal rivalries, career choices, that sort of thing. But one item really got a hold of me, and that was the idea of mode bits. The leader of the effort on developing this new minicomputer was Edson de Castro, and he was adamant that there would be no mode bits in the design. Mode bits led to feature creep. The design is harder to verify. The bits take on a life of their own. And the chief architect, Tom West, kept trying to sneak in mode bits. And so the story was along the lines of how do you deal with mode bits? What the interpersonal relationship that they had? How did they resolve these particular problems and still build a computer that was going to be performant? But what is RISC-V if not a huge collection of mode bits in the form of extensions, configurations, execution modes, whirl fields? You see this playing out in the tech config and the tech platform and the tech profiles technical groups. We have a plethora of mode bits that we have to take care of, that we have to verify. Good reasons to have these mode bits, and a common method to support these variations is a good thing, but it still makes trouble for the verification engineer. Now, verification techniques have improved greatly since the writing of the book and from the time I came into the industry. At the time of the writing of the book, stimulus was written in the form of static vectors. Checking was largely done with eyeballs. We were just beginning to understand and define what a scoreboard needed to be. Adding mode bits into this kind of testing was extremely painful. Well, today things have changed, and we can do a fairly rigorous evaluation of these permutations. We have the tools and methodologies to help us do our jobs. Now, you who are sitting in on this talk already know of ways of doing this. The one that we're going to talk about, the way Seagate approached the problem, is through the use of a constrained random verification environment. What are the test bench pieces that we have in our test bench? This is not meant to be complete, and it largely reflects the test bench that we built for our high performance core. We have the DUT in the middle in the white box with various pieces. On the left we have Fabric VIP and an external memory VIP. We have a register package. We have a retirement monitor that tells us what instructions are retired at any particular point. At the top we have a debug port VIP. And top right corner we have the VIP for verifying the trace encoder that we got from Ultrasoc. I'd like to, on this slide, emphasize 2 points. You guys are probably familiar with a test bench just like this, but there's something that I think was very valuable at Seagate, and it had to do with the use of the Fabric VIP and the debug port VIP. Within the DUT and how we tested the core, we'll talk about in the next slide. It's something that I'm sure most of you have already done. But one of the things that we did was that we tied existing Fabric VIP and some developed debug port VIP to inject stimulus into the DUT while we were executing code, so that we could do things like program buffer execution, single stepping, register reads, CSR reads, abstract debug commands, and interrupts. We wanted all of these things to perturb the execution of the core and see if it responded correctly. This diagram shows our random instruction sequences and how we did the scoreboarding of execution. Our instruction generator came from Valtrix systems. We would generate tens of thousands of ELF files that we would then run on Seagate's RTL simulation. The output from our RTL simulation would yield two logs. The first one is the raw trace log. What did the retirement monitor say as we retired instructions? We also had the trace output from the trace encoder, which also went into an instruction trace log. On the right-hand side, we used Imperis's RISC-V OVP sim as our golden model. It was the go-to model for us, which in turn also put out a trace log as well. We have our scoreboard was actually done with Perl script, where we did trace compare, which would give us pass or fail. And it was checking instruction sequences. Now, at exception boundaries, we also did some checking of CSRs. In general, because of the asynchronous nature of things like interrupts, trap handler tracing was filtered out by the trace compare script. What we were really looking at was, can we interrupt the processor, execute a program buffer, do debug commands, take an interrupt in return from it, and still keep the flow of instructions correct with respect to Imperis's RISC-V OVP sim. I'd like to take the two slides that we just talked about and tie them together and give you the main point of this whole talk. What did we do? What do we think we did right? We took our existing Fabric VIP that we had used on other projects within Seagate, other SoC projects in Seagate. We developed debug and trace VIP, and then we tied them to our third-party tool for random instruction sequence generation. And then, during code execution of that random instruction sequence generation, we would inject random stimulus, like debug abstract commands, program buffer execution, single stepping, interrupts. And then we would compare the instruction sequence with the instruction sequence we got from the architectural model. And we did this over thousands, tens of thousands of tests on a nightly basis. I'd like to talk a little bit about the tools that we found and brought into our environment and how useful we found them. First tool I'd like to talk about is Sting, which comes from Valtrix systems. It's a constrained random instruction sequence generator. It's constrained in the sense that you can provide snippets that allow you to focus a test on particular sequences. Now, you can generate your own snippets if you like, but mainly we took the snippets that they gave us and ran with them. And when we found coverage holes, we asked for specific sequences. This is coverage-driven verification, and it's profoundly useful. The golden model that we used came from Imperis, the RISC-V OVP sim. And like I said, it is the linchpin. It was our go, no-go model. Now, the Valtrix Imperis combination formed a very useful informal partnership. Our primary feedback went to Valtrix. When we had a problem, when we found a bug, when things didn't look right, we'd go to Valtrix, who was the instruction generator, who, if they thought there was a problem with the OVP sim, would forward those requests to Imperis. And we wonder if Imperis is aware that Seagate was the source of many requests that came from Valtrix. We met regularly every other week with the Valtrix engineers, and we got deliveries from there on a near weekly basis. The relationship has worked very well for us. The random instruction generator, Sting, has provided excellent functional coverage with which we use to measure our environment, which we use to measure in our environment. The architectural model helped us find many bugs in our cores. We iterated over this, it flagged bugs, we fixed bugs. So what were some of the other tools? These are ones that you'll be familiar with, I'm sure. The GCC tool suite, duh. That's what we use to compile the instruction sequences, and we have many directed tests, both C and assembler. This surprisingly led to yet another permutation that we had to manage. Different GCC tool chains had to be run on different OS versions. I know you're probably scratching your head. Our usual tool chain could run on both OS 6 and 7. However, for the toolchain that supported bit manip, it would only run on CentOS 7. Bah! Mode bits propagate in some unusual ways. We ran the RISC-V architectural tests, which were once called compliance tests on our cores, but they yielded no bugs. We synthesized our cores and ran them on an FPGA platform, actually platforms, and I'll talk about this a little bit more in another slide. We used UVM along with System Verilog as our methodology to follow. We had a servo benchmark that we used to check out functionality and to benchmark the core. But we also ran the mbench benchmarks to ensure that the changes to the core and changes to the compiler toolchain didn't affect the system. What tools did we develop ourselves? Well, Seagate had VIP for the fabric that has been used in our SoCs. We took that fabric VIP and extended it and improved it. Why? Because we have access to the source code. Yay! We developed trace encoder VIP with much help from Ultrasoc. We developed the TE initialization code in both C and System Verilog. We also implemented the trace decoder based on the pseudocode given to us from Ultrasoc. That took quite a while to get that working correctly, and it helped expose some bugs. I'll get to that later. We developed debug VIP. We synthesized and ran on an FPGA, and I really don't want to underemphasize this point. Sometimes the FPGA effort gets put on a back burner. Too hard to do, takes too long. We made good use of FPGAs in our design. We used 3 different platforms. We used a Xilinx VC707 for the high performance core. We used a Digilent Arty A7 for the area optimized core. And we also used an internal platform based on the Vertex 7 for both cores. We were able to attach the Lauterbach tools to it. We built and ran Zephyr on it. We built and ran an experimental TensorFlow Lite package on our HPC. All of those we got tremendous mileage out of on the FPGA. We felt very good about the core design because it was doing a lot of code execution. We developed interrupt-related VIP for both the PLIC and the CLIC. We have randomized UVM tests that were used to stimulate, to generate stimulus. And we did have directed UVM test and C-ASM test for particular directed tests. All this effort, the big question is, how is it that we got to keep our jobs so far? Well, we got First Silicon back, and within a few weeks of the chip arriving, our servo firmware was up and running. In other words, a real app running on real hardware doing real disk accesses. The debug connection works. We're able to start and stop, do all the things you would like to do with the debugger. And we found no defects in the core as of the writing, as of this presentation when I put it together in November. We're pretty jazzed about the results. What other results can we report out? We found a number of RISC-V specification issues that we reported back to the various technical groups. In instruction trace, a group that I was involved in, we found a problem with trace reconstruction during exceptions. The spec was changed to put in the information that was needed. We also found a problem during certain jump branch sequences. Trace reconstruction was incorrect when compared to Imperis's model. We debugged it with Ultrasoc, and the spec was changed, and the trace decoder pseudocode was changed. I'll emphasize that all of this came because of Sting and the Imperis model and our ability to track instruction execution. And Sting found all the interesting boundary conditions. We were also involved in the tech debug group. We found a conflicting ambiguous definition of auto increment on the system bus. Seagate and Lauterbach interpreted things differently, and that had to be resolved. We were involved in the click definition in the tech fast interrupt group. Our Sting test generation found some undefined boundary conditions that needed to be resolved in the spec. And with regard to architectural testing and being involved in the tech compliance group, we didn't find any design bugs from our architectural testing, but we did find some issues with the compliance frameworks and gave feedback to the tech compliance group. As I mentioned at the start of my talk, I was a relative latecomer to the project. The folks that did the majority of the work are probably right now doing real work and letting this old engineer brag about them. They're the ones who gave us functional silicon. So thanks for spending time with me. I wish we could have done this talk face to face. There's a lot of you I'd like to meet and chat with. So from Minnesota, I say goodbye and stay warm.